Has this ever happened to you?
I need to measure strain. I guess I'll use my strain gauge. Oh, no, not my $500 strain gauge. If only there were a way to measure large strains.
Or what about this?
I want to read a variety of strains on this planar surface, but I don't have enough voltmeters.
Well, do we have a new product for you? I'd like to introduce a new technology that will revolutionize strain measurements, digital image correlation. Digital image correlation uses digital photographs of a surface under load and pattern correlation algorithm to measure full field stress, strain, and displacement. To help explain this new technology, we have prepared a short educational video to explain how it works.
Structures under forces are commonly modeled by finite element analyses. The object is split into many elements, and properties such as stress and strain are calculated when the forces and boundary conditions are applied. Stress represents the intensity of the force, and strain the intensity of the deformation. From these results, we can see where a material would fail, displayed in an easy-to-read format. This method provides pretty visuals for sure, but it can't possibly translate to measuring real stresses on physical objects, can it? But of course, with modern developments to optical measurement methods, this revolutionary technique is called digital image correlation. This indeed sounds complicated, but once we understand its principle, it is wonderfully simple. First, the material is textured with a high contrast pattern for the algorithm to recognize, and a calibration image under no load is taken. The range of measurement is incredibly flexible, only dependent on the camera lens and the area being photographed. Next, forces are applied and photographs are taken at regular intervals with sufficient lighting as to help the algorithm detect edges. The more data captured, i.e., the more numerous the pictures, and the higher the resolution of each, the higher the sensitivity of measurement. Finally, the correlation algorithm is applied to the pictures to measure the displacement of the applied speckles. To understand the correlation algorithm, we may take a closer look at how they function. First, the software splits the photographs into small regions of interest. It will recognize points within these regions between photographs based on the speckle pattern. As the regions are small, deformations may be approximated as linear. There are 6 base distortions of which every linear deformation is comprised: XY translation, XY stretching, and XY skewing. It will then optimize the positioning of the points by combinations of those 6 transformations. The deformation map can then be converted into a strain map and colored for easy viewing.
If you're still not convinced, we have many satisfied customers willing to share these experiences. Hi, our team has used DIC to monitor displacements in railways and bridges and for measuring crack openings in civil engineering components. By using DIC and taking pictures regularly, we can investigate the projects in long term. So we need something that has a large range, since the civil projects are normally massive, but not necessarily the high time sensitivity. Most importantly, we need it to have high flexibility, which it does. It's likely to have different lightning conditions during the long-term analysis. We're not talking about a simple uniaxial tension test in a lab that can be done within 2 minutes. The difference now is this test will be performed for 10 or even 20 years. In these cases, either ZNSSD or ZNCC technique is used, since they offer most robust noise-proof performance and are insensitive to the offset or linear scale lightning fluctuations.
Hi, we're a biomedical research company specializing in bone replacements. We need to analyze the displacements and stresses on the bone-cement prosthetic interface. The measurement needs to be flexible so that patients can come in and get checkups and results can be overlaid and compared, but also sensitive so accurate individual tests can be done and small changes can be seen. Digital image correlation fits all those criteria and is perfect for our needs. We can even use second-order transformation algorithms, compensating for the lack of speckle in the bones. It's as sensitive as we want because of our cameras, and the software does an amazing job of matching images even if they were taken weeks apart.
Hi, I'm working in a material lab. We have used DSC to examine a diverse range of material specimens, including examining the evolution and uniformity of strain and materials testing, crack tip and crack propagation studies. We really appreciate its high spatial and time sensitivity, which can accurately describe the material behavior before and during the failure very well. For example, if a structure such as a reinforced concrete bar cracks, and it can be quite easy to see the location of the main crack. However, other small cracks may also be present, which are not really seen. Before we use the dye to identify more cracks, but in a labor-intensive, messy fashion, the output from the DSC as a map of local deformation shows cracks not visible to the human eye in a non-contact, low-cost fashion. It can provide accurate crack opening measurements even if the edges of a crack aren't well defined, and provide a useful information on where to fit crack opening sensors.
I'm a professor for a solid mechanics course at my local university, and I find digital image correlation to be a very useful tool for teaching. My students learn about finite element analysis, and it is great for comparing the results from the simulations to the results from real loading. It can also illustrate stress concentrations, for example, the necking of a ductile material or the fracture of a brittle material, improving on the uniaxial tension tests for the students. I can even demonstrate those without failing the materials. And after I started using digital image correlation for demonstrations, I've been getting 100% on all my course evaluations.
And if you call in the next 30 minutes, we will throw in another one completely free of charge. And we will also include a speckle spray and a high-quality camera with all the properties you need so you can get started immediately, all for free. And this camera, it has no image distortion, high resolution, and high dynamic range. This is the 1,000 value of the whole package, now only for 10 easy payments of $99.99. This package deal won't last long.
Disclaimer, this method may not work well if your speckle pattern is not obvious enough, if the image is distorted, or if there are noises during image acquisition and digitization. Inaccurate results may arise if photographs are taken over long intervals and large displacements occur, which may mess up the correlation criteria. When you use the 2D DIC method, this will not work well if the CCD target is not parallel to the object surface or you want the out-of-plane displacement. Ask your engineer if digital image correlation is right for you.
What are you waiting for? Get this limited time offer now!